Hi, we present towards unsupervised object detection from LiDAR point clouds. First, here's a 1-minute summary of our paper. Given sequences of LiDAR point clouds, we aim to train an unsupervised object detector without any human supervision for the application of autonomous driving. To achieve this, we first perform point clustering in the near range to produce initial pseudolabels and utilize translation equivariance of convolutional nets to obtain long-range pseudolabels as well. Given pseudolabels of the full range now, we utilize an unsupervised offline tracker to find object tracks and apply trajectory level refinement to ensure that every object has the same physical size across time. We discard short tracks and refine long tracks to produce pseudolabels for the next round of self-training. And after a number of self-training rounds, we get our final unsupervised object detector, Oyster, which stands for Object Discovery via Spatio-Temporal Refinement. Supervised object detection now works remarkably well when given a large set of annotations, both for pixel images and for LiDAR. However, most existing data is unlabeled, and obtaining human annotations is a costly and tedious process. As supervised learning starts to plateau, human annotations are increasingly the bottleneck for data-driven learning algorithms. Moreover, humans and animals can learn to perceive objects without explicit labels at all. This naturally inspires us to ask whether we can design unsupervised learning algorithms that discover objects from raw streams of sensor data. In this paper, we study unsupervised object detection from LiDAR point clouds. Point clouds are important for self-driving perception, and there has been a lot of work on supervised detection. Recently, some methods have tried to tackle unsupervised detection as well. Those methods either assume repeated traversal of the same location, which restricts what data can be used, or they can only detect moving objects in the near range. Our proposed method does not suffer from those limitations. Point clouds naturally give us a lot of object priors, especially in the near range, because there tend to be clear object clusters when point clouds are dense. However, in the long range, object patterns are less obvious due to sparsity. We also know that objects tend to move in a temporally consistent way. How can we leverage those priors to design scalable learning algorithms for unsupervised object detection? We propose Oyster, Object Discovery via Spatial-Temporal Refinement, for unsupervised object detection. Oyster has two stages, the initial bootstrapping stage and the self-improvement stage. In the initial bootstrapping stage, we use point clustering in the near range that gives us reasonable initial pseudolabels to kickstart the learning process. In the self-improvement stage, we leverage temporal consistency of object tracks to design a self-training loop that teaches an unsupervised detector to iteratively self-improve. Our goal in initial bootstrapping is to train a detector on near-range clustering pseudolabels only, such that it can zero-shot generalize to longer range before the self-improvement process starts. We use unsupervised tracking to filter out temporally inconsistent tracks from clustering pseudolabels. And then we design a data augmentation to mimic the LiDAR sparsity in the long range by randomly dropping LiDAR beams. We enhance this data augmentation by dropping rows and columns in the range view as well. Using those novel data augmentations, we train a COMNet on near-range bird-eye view LiDAR images, and then utilize the translation equivariance of COMNets to achieve zero-shot generalization to longer range. The model outputs give us the initial round of self-produced pseudolabels before the self-improvement process starts. The self-improvement stage can be summarized as track, refine, retrain, repeat. We first do unsupervised tracking, and then for long tracks, we relabel the bounding boxes to be temporally consistent, meaning that the same object should have the same size across time. For short and inconsistent tracks, we ignore them during retraining. The bounding box relabeling process uses a corner alignment technique, which is based on the intuition that the bounding box corner that is the most observed is likely to be the most reliable. We visualize the evolution of those self-training pseudolabels. The initial clustering pseudolabels are very noisy, but they contain useful learning signals. After initial bootstrapping, our detector can already discover new vehicle labels not captured in the initial clustering pseudolabels. With more rounds of self-training iterations, our detector discovers more vehicle labels and cyclist labels as well, and in general improves its IOU. Therefore, our Oyster framework constructs an object discovery loop where the detector is iteratively retrained on pseudo-labels of increasingly higher quality as self-training goes on. We also introduce a novel planning-centric perception metric based on distance to collision. We observe that it can sometimes be difficult to predict the full size of the objects in detection. What we really care about from the perspective of planning is to correctly predict objects' distance to collision from the ego vehicle. So we formalize this intuition in the proposed DTC-based AP and recall. We evaluated our unsupervised LiDAR detector on two real-world self-driving datasets, PandaSet and Argoverse 2. We compared our unsupervised detection method against a variety of prior unsupervised baselines and showed that on both IOU-based and DTC-based metric, our method significantly outperformed prior baselines. We see that dbScan clustering tends to struggle with long-range sparsity. Persistence-based clustering improves long range, but it is worse at detecting static objects. The previous state-of-the-art Modest also struggles to detect static objects. Our method, Oyster, is the only one that can provide high-quality detections at range. And we see the same across many different sequences on both PandaSet and Argoverse. In conclusion, we propose Oyster, a novel framework for unsupervised object detection from LiDAR point clouds. We show that self-supervision, based on temporal consistency, can be combined with weak object priors to enable scalable object discovery, which significantly outperformed prior methods. Our work is another step towards robots that make sense of our visual world without human supervision.